Well, hello. Today's topic is highway engineering curves. We're going to look at a calculation to do for some curves on a highway. Those of you who want into civil engineering for highways, you will use this pretty regularly and need to understand it deeply. Those of you who are going to highway construction, and there will be a lot of that in Cincinnati over the next many years because of the new bridge and the infrastructure money that's being that has been obtained and taxed and approved and all of that. So you're gonna be seeing, some of you are gonna be seeing a lot of highway construction, and I just wanted to kind of give you a brief introduction into some of that so that you've got an understanding. This is a set of plans for Interstate 75 done a number of years ago. Went through St. Bernard area, and I wanted to show the class something here at the end. We've been talking about this, and here's our roadway and our plans. But here on the back, it's under the basis of bearings. It talks about NAD 83, North American datum in 1983, and this is the 95 system. It's an older system. And then the vertical is on the 88 system. We've been kind of talking about that. Those need to be well listed and understood that we are working off of what datum we are using for coordinate systems. And then, like we did a couple of classes ago, we had to come up with a conversion from the grid to ground. And actually, in class, we went ground to grid, but all of this is drawn in grid, or on the state plane coordinate system. So it says to go from grid to ground, we have to multiply by a project adjustment factor of 1,000,000,008,341,406. And what that means is that if we are going from distances that are on the grid, we have to multiply by this number to get to what we would measure on the ground. Look at this number: tens, hundreds, thousands, 10,000s, and just a little bit more. So what we're saying is we're around 1 in 10,000 even with these numbers. And we are making it longer because we're going from the grid up to the ground. In class, we went from the surface down to the grid. So we had a 0.9999, literally the reciprocal of this number. Is that a big deal? Sometimes, sometimes not. For something like a roadway, however, where you're going, many, many miles, that becomes quite significant. Even within 1 mile, 5,280 feet, you were literally about 6 inches, half a foot, in a mile. And as you begin to accumulate that, that becomes very, very significant. So I wanted to point that out. There's reasons for what we're doing, and long term, hopefully you're beginning to see those, or you will see them. That aside, today's topic is about curves, and we're going to be looking at ramp D. And you'll notice that we've got a straight and a straight, and here's my ramp. It's got a curve that is in it, and we are going to be going from this section of curve around station 112, looking at this arc going up to station 117. If I go to one of the earlier pages, they've got a little bit larger detail of that, going from my curve to straight. So we got a straight and a straight curve in between it. And they've listed the data for that center line curve right here. And I'm going to explain what this means. I've transferred that to this piece of paper, which we are going to, I will upload so that you have, but this is what we're going to do our computations on. So I have a little diagram, and this is the center line of the roadway coming in, center line going out, And we have a curve, and this is a true circular curve. I mentioned something about spirals and things in the class, but that's really not critical. I just want to get to the circular curve here today and take a look at the computations that go along with it. So if I were to simply draw this curve in here, and I've given you the center of the circle, the center of the curve. This is an unobtainable point. I mean, if we look at our radius, we're 1,400 feet away. So this is always going to be way off the site in somebody's property or who knows where. It's physically unobtainable. You can't get there to do anything with it. It's just for computation purposes. So let's look at some of these words and terminologies that we have up here. So somewhere at this end is the beginning of the road project called 0, 0. And I know that because we're coming in straight. We're on a straight line somewhere, at least in this little bit, and we begin our curve. This PC is called the point of curvature. It's where the road begins to make this turn. This is the true center line of the roadway that we are working on. So this is the pathway that we're following. When we get to the other end, we go straight out, or tangent out is actually the better word, because this is called the point of tangency. Or the PT, it's where it tangents out. Very fundamental is the fact that these are 90-degree angles. These are right angles in here. So the center of the curve tangents, touches at a 90-degree angle to the arc at the beginning and the end of it. And by definition, the PT is the end of it and the PC is the beginning. So we try to follow in a progressive manner along the stations as the stations are labeled. If we extend both of those straights, we come to this place up here, which is important because it's called the PI, or the point of intersection. And that's what was given in the data of the curve, the point of intersection, the coordinates and or whatever of that is referenced to this PI. Well, there's a couple of fundamental things that we need to look at. One is that this is an arc length. And it's labeled as L. It is the distance as though we were to take a wheel and go right along there, or to take a tape and measure along here, and continues on that center line. This angle that is formed down here is called delta, or I, and is known as the central angle. Some people use the letter, or the symbol delta, some use the letter I. And this is called the degree of curvature. In fact, and let's put this in here since we've got it. In our case, this is 19 degrees, 52 minutes, and 57 seconds. We're going to go ahead and label this up as station 115 plus 1631. So what we need to do is we need to kind of begin to think about some of these computations. This is called degree of curvature. For this class, that's not a big deal, but by definition, what that means is if I had 100 feet of this curve in here, it would subtend, or it would make a 4-degree arc in here as an angle. Not a big deal for us. In fact, I'm going to kind of erase that so that it doesn't get in your face too much more than that. All right, our curve has a radius. It's 1,432 feet and some change. Now, this is one time where we use radiuses because it truly is. It's not a diameter. So we do use radius here. So a fundamental concept then is proportioning. So if I have a circle and I have some proportion of it. Now, in high schools, they beat you to think that everything is perfect, a fourth, a half, an eighth, a ninth, a 16th, whatever. And the reality is it's not. They're always screwy angles, okay? So the concept, however, is that the length of the arc is proportionate to the angle that it makes. In other words, we know that a complete circle is 360 degrees, and we know that the distance all the way around the circle is called the circumference, which is equal to 2 pi times the radius. So we can say that the arc length is a proportion of the circumference, the same as delta angle is to 360. Not hard, you just have to think about it, and that makes a lot of sense. Now, the issue is that we're not dealing with halves and fourths or anything, we're actually just dealing with angles. So if we set this angle in here, we're going to have 1952.57 is to 360 degrees, and the same portion as L is the 2 pi times 1432.39. 1952.57 divided by 360 degrees times 2 pi 1432.39, and the arc length then is 497.06 feet. That's what they've given to us. So we've computed that number and it checks. So the length of this arc is 497.06 feet. And I'm going to put this down here. On my answers. All right, so the rest of these numbers are really nothing more than trigonometry. Even though it's a circle, we're going to use a triangle to solve it. So if I simply draw that, you see that you get a right angle. This distance across here is labeled as t. The word is tangent. Proportionate, this thing is symmetrical. And all we need to do is to remember our trig functions. And sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, and tangent is opposite over adjacent. Because if you look at this, if I take half of that angle, of the central angle, 1952.57 divided by 2, 956.28. I can say that I can calculate t by taking the, let's see, I've got opposite over adjacent. Oh, that's tangent. Guess what? It's called tangent. Let's do that calculation right here. So the tangent of 956.28 and a half is equal to t over the radius, or my side adjacent, of 1432.39. So I take the tangent times 1432.39, and I come up with a calculated value that t is 251.05. They gave me t is 251.06. I don't quite agree with it, but it's close enough for what we're doing. So this t is 251.06. And just because, I'm going to go ahead and put it down here. Well, what that means, what we can do then, is we can go from the point of intersection, we can go backwards towards 0. We can go backwards and get the station of the PC. So we can take 115 plus 1631, station of the PI. And whenever we're dealing with stationing, really all we do is get rid of the plus sign. So I guess I can be dramatic and do that. Actually, I think I'm just going to rewrite that. And I can subtract 251.06, which was the tangent, and that will give us the station of the PC. And that gives me 112.6525, or in station terminology, 112 plus 6525. Now, we want the station of the PT. What you cannot do is you cannot add the tangent and get here. You cannot do that. No, cannot do that. What we have to do is we have to take the station of the PC and then work along the curve to get to the station of the PT. It is not the same distance here, here, plus here, here, as it is from here to here. So you say, well, why don't we take half the arc and get backwards? I understand, but it's not how it's done. Okay, it's by definition and is not how this thing works. So when you get to highway engineering, maybe they'll explain it better, but I'm just telling you, it's how it is. So you gotta know it. You gotta memorize it. So if I take the 112.65 and add the arc length of 497.06, I now get the station of the PT. So if I take the 112.62, get rid of the plus sign, treat it like a number, add 497.06, I get 117.6231, which is the station of the PT. And that is correct. So one last element on here, actually two, one last primary element that we would look at, and that is the distance between the PC and the PT. If I connect those as a straight line, this is called the chord. And you'll notice that by drawing that, we get another right triangle in here, actually two. And if we solve for this distance, I'll call it x, and I'd have x over here. If we add them together or double it, we actually come up with the chord. So we're going to use this right triangle here to solve for x. So we have the angle, we need the opposite, and we have the hypotenuse. So angle, opposite, hypotenuse looks like it's the sine function. So if I take the sine of 9 degrees, 56 minutes, 28 seconds is going to be equal to x over the radius of 143239. Notice that now with this triangle, that's the hypotenuse. It's the longest side. So let's go ahead and do that. 9, 56, 28.5 sine times 143239 equals 247.285. You'll think about this a minute. I would imagine that this curve, this chord is going to be less than the arc length. I think the distance across here, the chord, will be less than the arc. So if I multiply this by 2, double it, I come up with the chord length of 494.57. So the straight line of distance across there is indeed less than the arc length. Let's go ahead and put that down here. All I did was put it in my score sheet. Okay, there's one other piece of this, and that is this little distance called E, or the external E. And now, if you think about this, if I use that same triangle and solve for, I'll call it Y, and subtract it from the radius, I would get then this E. If I take the radius, subtract out the Y, I get the E. All right, since I've got a little bit more blank space over here, I think I'm going to solve it right here in the middle. So adjacent and hypotenuse is going to be cosine. So the cosine of 9, 56, 28, let me move that down a little bit, is equal to y over the radius of 1432.39. And if I solve for the y distance, I get 1410.88. So this is 1410.88. And if I subtract that from the radius, I get 2151. Now, they get 2183, and I don't know why. I disagree with that number. Now let's think about why that would be important. If this is 2151, typically you're not dealing with highway curves when you're using that number anyway. Typically, you're dealing with something like a radius in a parking lot, maybe a small street in a subdivision, something like that. So the surveyor would actually give you the PC, some physical point, a hub in the ground or something here. Likewise, they would give you the PT, again, a hub in the ground or some point right here. And then the contractor especially would be able to then pull a string or a straight line across this cord. And at the midway of the cord, or actually that X distance, they could make a note of this point here, where that is, and then measure out that E distance, 21 and some change feet, and actually have another point on the curve to help them build it. And frankly, you could do that a couple of times, depending on how long the cord is, the curve is. You can actually do that a couple of times, calculate it, and then you would have multiple points to string an arc to make the curve go along in there. So there's some value to that. This is a complete job of the calculations. I will go ahead and post that, and you can go through it yourself and try it to see where things come from. And then I have also given you one to work on your own. We can take a look at that on the next class. So again, you can try with these calculations. I will post these. You can try them. By the way, that's degree of curvature. You can try those and use these formulas if you like. I don't think they're necessary. If you know right triangle trig, that should be all you need to know. So give it a shot, and we'll see you next class.